review the laws of exponents, and this will be done in lesson 1, while in lesson 2 we would focus on the simplification of exponential expressions as well as solving exponential equations. In lesson 1 we review the laws of exponents. The outcomes for this lesson. In this lesson we will firstly revise the use of the exponential notation. Secondly, investigate the laws of exponents or indices. And finally, apply the laws of exponents or indices. We review the exponential notation, and we will also utilize the calculator to some extent in the following investigations. Consider the 4 examples. In the first example we have 2 to the power 4, which simply means that we multiply the number 2 4 times by itself. In a similar way, 3 to the power 5, in this case we multiply the number 3 5 times by itself, and so on. Now if we use the calculator in the first and say the last example, if I multiply the number 2 4 times by itself, as indicated on the screen, and do this calculation, obviously we get the answer of 16. What we are interested in at this stage is that if we take this number 16 and write it in terms of its prime base, so I use the prime factorization, then clearly from this calculator response we can see that if we multiply the number 2 4 times by itself, it is equal to 2 to the power 4. In a similar way, considering the last example, if we take the number 7 and multiply it 3 times by itself, we get the answer. But again, if I convert this answer of 343 and write it in terms of its prime factorization, then clearly the calculator indicates that 7 to the power 3 is the same as 7 multiplied by itself 3 times, or 7 multiplied by itself 3 times is the same as 7 to the power 3. So what can we conclude? We can conclude that 2 to the power 4, which really means you have the number 2 multiplied 4 times by itself, can be expanded as 2 multiply by itself 4 times. In the same way, 3 to the power 5 is identical to 3 multiply by itself 5 times, while 5 multiplied by itself 4 times can be written as 5 to the power 4. In a similar way, 7 multiplied by itself 3 times can be written as 7 to the power 3. We can therefore conclude that if we have a to the power 5, then this means we multiply the number a 5 times by itself. Or sometimes we simply say we have 5 factors of a. And in a similar way, if we multiply the number b 4 times by itself, it can be written in a short way as b to the power 4. So really this notation enables us to switch between the expanded form and the shorter version. You should be careful, however. If we look at 5 times a, then this is simply the number, here we simply take the number a and add it 5 times to itself. While if you take the number b and you add it 4 times to itself, then we can write this as 4b. For instance, think about you go to a shop and you pick a banana and a second one and a third one and a fourth one, and you put them in a packet. You will have 4 bananas. In general, going back to the exponential notation, we can say that if we have a to the power n, we can expand this as a multiplied by itself n times. Or if you have the number b and you multiply it by itself m times, we can in short write this as b to the power m. So far, we consider numbers a and b. In this case, the a and b are called the base, and they can be any real number. While the numbers n and m, in other words, the index numbers, at this point of time must be an integer. If you see a to the power n, then we read this as a to the power n. In a to the power n, we refer to this a as the base and to n as the exponent or index. We investigate our first index law, which is really the index law for multiplication. You can also use your calculator to confirm some of these results. Consider the 4 examples. If you have 2 to the power 4 multiplied by 2 to the power 3, now remember that according to the notation, the first number 2 to the power 4 means you multiply 2 4 times by itself, and in turn this we multiply with a number equivalent to 2 multiplied by itself 3 times. So in total we multiply 2 by itself 7 times, and from the notation we can write it like this. Important what we notice here is that if we multiply and the bases are the same, to get the final answer we write down the same base and we simply add the 2 indices. This is exactly what happens in the second example. The third and the fourth example slightly more different, or more or less the same thing, but just in starting with the expanded notation. In number 3 we start off with the product of the number 5 multiplied by itself 4 times, and this in turn we have 5 multiplied by itself 3 times. Of course, according to the exponential notation, you can write it like this. But then it is clear, if we remove the brackets, you can remove this bracket, then we simply see that we have the number 5 multiplied by itself 7 times. So therefore, a similar observation as we've made before, that if we multiply and the two bases are the same, like in this case it's 5, then in the final product we still have the same base 5, and the index number for the product is simply the sum of the two indices. Using my calculator I can just confirm, say, one of these results. Let us take the first example. If we have 2 to the power 4 and we multiply it by 2 to the power 3, we get an answer. And if I convert this particular product or write it in terms of its prime base, then clearly on the screen you will see that 2 to the power 4 multiplied by 2 to the power 3 is the same as 2 to the power 7. So what can we formulate? We can formulate that if we have a to the power n and we multiply it by a to the power n, then this product will be a to the power n plus m. So what does this rule really state? It simply says that if we multiply two powers, in other words numbers in the exponential form, and the bases are the same. Now these two facts are the conditions, namely you must multiply and the bases must be the same. Then the rule states that to obtain the resultant product, in the product the base must remain the same, while the index of the product is the sum of the indices. Let us look at some numerical examples connected to the index law for multiplication. You can afterwards use your calculator as a checking device. So if we look at the first example, 2 to the power 5 multiplied by 2 to the power 4. Note the two conditions are met here, namely that we do multiply and the bases are the same. And then the rule simply states that in the final product, the base will still be 2, while the index of the product is the sum of the two indices, namely 5 plus 4. Okay, and then of course you can switch to prime factorization, and then it will show that your calculator will show you that this result can also be written as 2 to the power 9. In a similar way, if we multiply 3 to the power 5 with 3 to the power 6, multiplication, same basis, it will give us an answer of 3 to the power 5 plus 6 or 11. Even when the base is minus 2, remember, it's still a real number, or if the base is a third, the same rule will apply. So you get minus 2 to the power 5 multiplied by minus 2 to the power 4, and this then results into minus 2 to the power 5 plus 4 or 9. Just a bit of advice here: if you use your calculator as a checking device, if you calculate this answer here, as you see this expression, you'll get minus 512. Please do not try and switch to prime bases here. It will only be applicable for a positive whole number. But then what you can do to check your result is, in addition, also go and calculate minus 2 to the power 9. So minus 2 to the power 9 will give us an answer of minus 512. And in the same way, minus 2 to the power 5 multiplied by minus 2 to the power 4 will also give an answer of minus 512. And a similar type of test can be conducted here. So a third to the power 5 multiplied by a third to the power 6 give us a third to the power 11. And both these results will give us this particular fraction. Of course, it's important to note that you can also apply the law in a reverse direction. So in other words, if I have 2 to the power 9, I can partition it into 2 to the power 5 multiplied by 2 to the power 4, because the bases are the same and you multiply, so you will again end up with 2 to the power 9. And here we can also split it up as 2 to the power 3 multiplied by 2 to the power 6. There is lots of other possibilities. In a similar way, 3 to the power 11, just giving you two possibilities here. You can split this up as 3 to the power 5 multiplied by 3 to the power 6, or partition it as 3 to the power 7 multiplied by 3 to the power 4. Let us consider a few algebraic examples where we apply the index law for multiplication. Firstly, a to the power 5 multiplied by a to the power 4. Two conditions are met, namely we multiply and the bases are the same. So this will then give us a final answer of a to the power 5 plus 4, or a to the power 9. In a similar way, b to the power 5 multiplied by b to the power 6 will give us b to the power 5 plus 6, or 11. A little bit more of a complicated example. Here we can rearrange the terms, because remember, the commutative property or law will be applicable for multiplication. So I shift it slightly so that we can then group a to the power 4 multiplied by a to the power 6 together, and in the same way we can group b to the power 5 and b to the power 4 together. It is also true that the associative property will be applicable for multiplication. So if I make this rearrangement and regrouping, then we get a to the power 10 multiplied by b to the power 9. In a similar way, using the commutative property followed by the associative property, we can get the a to the power 3 next to a to the power 4, or multiply the 2, so you get a to the power 7, while we have b to the power 5 multiplied by b to the power 6, or b to the power 11, c to the power 6 multiplied by c to the power 7, which is c to the power 13. And this is as far as you can go. Applying this law in a reverse direction, if we have a to the power 12, then there's lots of possible ways of splitting this. We can say it's a to the power 5 multiplied by a to the power 7, or a to the power 10 multiplied by a to the power 2, and many more. And in a similar way, if you have a to the power 12, b to the power 15, then we can split this a to the power 12 up into a to the power 7 times a to the power 5, and b to the power 15 you can write as b to the power 5 multiplied by b to the power 10, for example. And then applying the commutative and associative property, then you can say we have a to the power 7 multiplied by b to the power 5. This in turn gets multiplied by a to the power 5, b to the power 10. And there will be many other similar examples. Let us look at the second law, index law, or the law for the division of two powers. You can also utilize your calculator to some extent in these investigations. The first example, if we have 2 to the power 5 and we divide it by 2 to the power 2, then this will give us an answer of 2 to the power 3. What you can do is you can write this as 2 multiplied by itself 5 times divided by 2 multiplied by itself twice. And then we can simplify that fraction, and 2 of the factors of 2 will cancel out, and we'll end up with 2 multiplied by itself 3 times. So really it seems that if we divide and the bases are the same, when we simply subtract the exponent of the divisor from the exponent of the dividend, to obtain the exponent for the quotient. A similar observation can be made in the second one. Let us use our calculator to confirm, for instance, the second result. So I'm going to use the calculator to show that if I have 3 to the power 6 and we divide it by 3 to the power 2, I want to show that the answer is actually 3 to the power 4. So if we enter this, of course we get 81, and if I write this 81 in terms of its prime basis, then we get 3 to the power 4. So clearly, if you divide and the bases are the same, like in this case 3, then to get the final quotient, you simply rewrite the same base and subtract the exponent of the divisor from the exponent of the dividend. This is enough just to confirm this. So now we're in a position to formulate the index law for the division. That if you have a to the power n and you divide it by a to the power m, then it's a to the power n minus m. So what do we actually see here? Again, make sure that you understand the two conditions. Firstly, it is only applicable, or this law is only applicable, if we divide two powers or two numbers in exponential form, and they must have the same base. Can you see? You have a to the power n divided by a to the power n. So the first condition, it's division, and the bases are the same. Now, then how do we find the quotient? Firstly, in the quotient, remember the quotient is the answer to a division problem. The base remains the same, right? And to obtain the index for the quotient, you take the index of the dividend and you subtract from that the index of the divisor. So it's n minus m and not m minus n. Let us look at a few numerical examples where we apply the index law for division. You can, and I leave it for you, check some of these by means of your calculator. So if you have 2 to the power 5 divided by 2 to the power 2, then according to this index law, it is 2 to the power 5 minus 2, or 2 to the power 3, namely 8. 3 to the power 7 divided by 3 to the power 2 will give us an answer of 3 to the power 7 minus 2, or 3 to the power 5, which in turn your calculator will indicate as 243. Even when the base is not a positive integer, even a negative integer, it will still be true. So if you have minus 2 to the power 5, divide by minus 2 to the power 2, note the two conditions, its division and the bases are the same. Then it will give you an answer of minus 2 to the power 5 minus 2, which is minus 2 to the power 3, and this of course is minus 8. In a similar way, 3 to the power 4 divided by 3 to the power 6, which is then 3 to the power 4 minus 6, which is 3 to the power minus 2. And if you use your calculator, you'll see your calculator will tell you that this is 1 over 9. And 1 over 9, of course, is 1 over 3 to the power 2. So this already points to something that we will see later on, in this case, because the index of the divisor is greater than the index of the dividend, you get a negative index in the quotient, and this negative index can then be changed into a positive index. Please check this particular example by means of your calculator. Of course, the law can also be applied in a reverse direction. If we have an answer of 2 to the power 4, then this can be the result of division of 2 to the power 9 by 2 to the power 5, or 2 to the power 6 by 2 to the power 2, or 2 to the power 2 divided by 2 to the power minus 2. And in the same way, you can check the 3 examples as mentioned here for 3 to the power 7. Let us consider a few algebraic examples based on the index law for division. If you have a to the power 6 and you divide it by a to the power 2, then of course it's a to the power 6 minus 2, or a to the power 4. In the second example, b to the power 5 divided by b to the power 7 is b to the power 5 minus 7, or b to the power minus 2. We will discuss this at a later stage, because we normally would like to end up with a positive index. Third example, a to the power 4 times b to the power 5, everything divided by a to the power 6, b to the power 3. Note what is in the first bracket is your dividend, and what's in the second bracket is your divisor. And we can always write a division problem as a fraction. So really, we have the product of two divisions here. We have a to the power 4 divided by a to the power 6. And this particular quotient needs to be multiplied by b to the power 5 divided by b to the power 3. The reason why we group it like this, because this particular law is only applicable if the bases are the same. So clearly we get then a to the power minus 2 multiplied by b to the power 2. So if I apply something here straight away, this, remember, is your dividend, and this is your divisor. So this is above the line and this is below the line. Right, you can also think in terms of cancelling identical factors. So we get a to the power minus 1, which is 3 minus 4, times b to the power minus 2, of course it's 5 minus 7, and c to the power 2, because it's 9 minus 7. Applying the law in a reverse direction means that there is many ways in which I can rewrite a to the power 12. I can rewrite it as a to the power 15 divided by a to the power 3, because 15 minus 3 is 12, or I can rewrite it as a to the power 10 divided by a to the power minus 2, because 10 minus 2 gives me 12 again. And considering the product of two different bases here, raised to a certain power, we can take the a to the power 12 and split it up. As for instance, a to the power 17 divided by a to the power 5, because 17 minus 5 is 12, while b to the power 15, we can rewrite this as b to the power 5 divided by b to the power minus 10, because 5 minus 10 again gives me 15. This is just one of many possible examples. And then another way will be to write this a to the power 12. How can I get this? 7 minus 5, and b to the power 15 you get by saying it is b to the power 20 divided by b to the power 5. Please take careful note of these notations. This last one specifically, what is in the first bracket is your dividend. That will be above the line in a fraction notation, and what is in the second bracket is your divisor. So this will be the denominator if you write it in a fractional form, while this first one is the numerator in a particular fraction. Let us look at the third law. You could use your calculator to assist you in this particular investigation, but we should be able to get some idea of this index law. So what do we have here? We have 2 to the power 5, everything to the power 3. Now, from the index notation, you can say that this really means that we must multiply 2 to the power 5 3 times by itself. And thereafter we have a multiplication problem. So from the multiplication law, which states that if the bases are the same and you multiply, you must simply add the indices. So you get 15. And of course, looking back, we see this 15 is really 5 times 3. We could use the calculator to confirm this. Well, if we look at the second example, 3 to the power 2, everything to the power 4, from the index notation, this really implies that you multiply 3 to the power 2 4 times by itself. And then again, using the multiplication index law, it states that if the bases are the same, you can add the indices. Of course, we add them 2 at a time. Alright, so you get 2 plus 2 plus 2 plus 2, or 2 added to itself 4 times. So it's 3 to the power 8, or 2 times 4. So it seems that we need to multiply these two. So let us use our calculator to confirm the correctness of one of these results. Let us use the calculator in the second example. So we have 3 to the power 2, and this all raised to the power 4. And now I can switch or change this particular number, 6561, and write it in terms of its prime base. And that's 3 to the power 8. So clearly it then means that to get the final result here, you multiply the 2 by the 4 as indicated here. So we can therefore formulate the third index law in the following way, that if I have a to the power n, everything raised to the power m, then the final answer will be a to the power n times m. Please don't confuse this particular law with the law for multiplication. Let us look at a few examples where we apply this third index law. In the first example, we apply this index law twice. So 2 to the power 5 is raised to the power 3, and then this result in turn is raised to the power 2. So firstly we applied, so we get 2 to the power 5 times 3, and then raise this to the power 2, so it's 2 to the power 5 times 3 times 2. So really it means we multiply 5 with 3 with 2. So you get 2 to the power 30. Similar type of action will take place in example 3, where our final answer will be a to the power 5 times 3 times 2, or 30. In the second example, clearly we will get x to the power 5 times 4, or 20. Be careful about, in example 4, the index of the 3 is 2n plus 3, so the index must be multiplied by 4. Therefore, both terms in the index needs to be multiplied by 4, so it's 3 to the power 8n plus 12. So be careful about this one. Let us, just to finish this off, apply or use our calculator in example number 1. Right, let's try and show that this will be 2 to the power 30. So I've got 2 opening brackets here, and I have 2 raised to the power 5. So all I'm really doing here is just to type in this expression, closing bracket, everything raised to the power 3, and this in turn raised to the power 2. Okay, that's the answer. Converting it to prime factorization, or finding the prime factorization, we get 2 to the power 30, which clearly is 5 times 3 times 2. Let us look at law number 4, and we will look at this firstly by considering a particular example, which we can of course confirm the correctness by means of our calculator. So again, applying the exponential notation really means that everything that's in a bracket here is raised to the power 3. So what we have in the bracket here gets multiplied by itself 3 times. And then of course we can rearrange the factors and group the same bases together, so we get 2 to the power 5 multiplied by itself 3 times, and 3 to the power 2 multiplied by itself 3 times. And then applying the multiplication law twice, you get 2 to the power 10 plus multiplied by 2 to the power 5, which is 2 to the power 15. And in the same way, this will give us 3 to the power 2 plus 2 plus 2, or 6. Looking back, we simply note that to obtain 2 to the power 15, we multiply the 5 with the 3. And to get 3 to the power 6, we multiply the 2 by the 3. Note, it's important that you should take note that inside this bracket is a single term. In other words, this particular law will not apply if there is a plus or a minus. Let me get in the calculator to confirm the correctness of this numerical result. Right, so let us calculate this by means of the calculator. So we have 2 to the power 5 multiplied by 3 to the power 2 and all of this to the power 3. Right, so this is the initial expression. Calculating this, we get this quite large numerical answer, and then use your calculator to find the prime factorization, and we obtained exactly the result as we have seen here, namely 2 to the power 15 and 3 to the power 6. And we observe then, to get the final answer, we simply multiply the 5 by the 3 and the 2 by the 3. So we can now formulate this particular index law as you see on the screen. If you have a to the power n, b to the power m, all raised to the power p, you get a to the power n times p multiplied by b to the power mp. I just want to confirm or restate the importance that you should take note that you only have one term in this particular bracket. let us look at a few examples in which we apply index law number 4. In the first example, we have this expression here in brackets. Note it's a single term. So what does this law mean? It means for each of the bases we multiply its exponent by 5. So it's 2 to the power 2 times 5, or 10, x to the power 3 times 5, or 15, y to the power 4 times 5, or 20. Of course, 2 to the power 10 can be written in this numerical format. Again, there is a single term in the bracket in example number 2. So we raised 2 to the power 2 times 3, or 6, a to the power 3 times 3, or 9, 3 to the power 2 times 3, 6. Note, the base 3 is below the line, so it must remain there. You can't take it to the top now. And the same for b to the power 4 must remain in the denominator position, so you get b to the power 12. Of course, 2 to the power 6 and 3 to the power 6 can be written in terms of the numerical result. In example number 3, this minus is very important, because remember, if this power is even, then the final result will be positive, while if it's odd, it will be negative. The best is to view minus 5 as minus 1 times 5. So you have minus 1 raised to the power 4, because minus 1 to the power 1, multiply by that 4 gives me this. 5, there is no index indicated here, so we assume it's a 1. So it's 5 to the power 1 times 4, and a to the power 8. And of course, minus 1 to the power 4 is plus 1, and 5 to the power 4. If you use your calculator, you'll find it's 625. So the final answer is then 625, a to the power 8. Let us look at index law number 5, and again we could help use the calculator to assist us in this computation. Now, if we have 2 to the power minus 7, this can be, according to the division rule, a result of dividing 2 to the power 2 by 2 to the power 9. Of course, this can be written in a fractional form, and if we consider that 2 to the power 2 is 2 multiplied by itself twice, and 2 to the power 9 is 2 multiplied by itself 9 times, 2 of the factors of 2 will cancel out, and we will end up with 2 multiplied by itself 7 times in the denominator position, which you can write like this. Of course, in total, this really means if you have a negative exponent in a particular exponential notation, then we can make this positive by moving it from the numerator position to the denominator position. Of course, the opposite will be true too. If you have a negative index in the denominator, you can make it positive by moving it to the numerator position. Similarly, if we have 3 to the power minus 5, this can be the result of dividing 3 to the power 2 by 3 to the power 7. We can write it in a fractional form. We can cancel 2 factors of 3, and we will end up with 1 over 3 to the power 5. And therefore, again, we notice that if the index is negative, and we can make this positive by moving it from numerator, because this fraction you can write as 3 to the power minus 5 over 1. And we can then write it as 1 over 3 to the power 5. Or simply, we write it in this particular fractional form where the numerator is 1. Let us use our calculator to check the correctness of one of these results. Let's consider the first one. If we have 2 to the power minus, remember it's this one and not a subtraction, 2 to the power minus 7, then we see that the calculator tells us that this is the fraction 1 over 128. So 2 to the power minus 7 is 1 over 128. In the same way, if we take 1 divided by 2 to the power 7, we get exactly the same answer. So what is important here? That 2 to the power minus 7 is the same as 1 over 2 to the power 7. I would like to do the reverse one. Say we have 1 over 2 to the power minus 7. 1 over 2 to the power minus 7. What do you expect? Hopefully you all were predicting 128. So now the negative is there. So I want to show that this is the same as 2 to the power 7. So straightforward, if I calculate 2 to the power 7, we will also get an answer of 128. So we can therefore formulate index law number 5 as that if we have a to the power minus n, remember this is over 1, we can write it as 1 over a to the power n. So that's the way of making a negative index a positive index. And in a similar way, if we have 1 over a to the power minus m, you can write it as a to the power m. So in other words, if it's a negative exponent in the numerator position, you simply shift it to the denominator position and then you change the sign of the exponent. Or if there is a negative exponent in the denominator position, by shifting it to the numerator position, you will change the sign of the index. Let us look at a few examples where we apply index law number 5. If you have 2 to the power minus 3, it can be written as 1 over 2 to the power 3, therefore 1 over 8. Here the 3 to the power minus 2 must go to the denominator position, becomes 3 to the power 2, while 2 to the power minus 3 goes to the numerator position and becomes 2 to the power 3. So we simply get 8 over 9. If you have a fraction 2 over 3, note we can say that this is 2 to the power 1 raised to the power 3, so 2 to the power minus 3, 3 to the power minus 3. This 2 to the power minus 3 goes to the denominator position, while the 3 to the power minus 3 goes to the numerator position, and by doing so you change the signs of the exponent. So we end up with 3 over 2 to the power 3. Now here we get an important principle. If you compare 2 over 3 with 3 over 2, then 3 over 2 is the reciprocal of 2/3. Or the other way around. Now what happens? If you replace a fraction by its reciprocal, then we must change the sign of the exponent to which they have been raised. Right. And in both cases, whether you take this first or the second one, you get an answer of 27 over 8. You see, the exponential notation really only have meaning if this exponent is a positive whole number. So here this law allow us to change a negative whole number into a positive whole number and then apply the exponential notation. In example number 4, be careful, you have 2 to the power 1, so the 2 must remain in the numerator position. M to the power minus 2 goes to the bottom, or to the denominator position, becomes m to the power 2. 3 to the power minus 2 must go to the numerator position and becomes 3 to the power 2. N to the power minus 3 goes to the top and becomes n to the power 3. And now all the exponents are positive, so we can apply the expanded notation, or simply the exponential notation. And 2 times 3 to the power 2 is 18, so you get 18n cubed divided by m squared. In the last example, we only need to move a to the power minus 3 and b to the power minus 5. So b to the power 4 and a to the power 7 must remain in their original positions. B to the power minus 5 goes to the top, becomes b to the power 5, and a to the power minus 3 must go to the denominator position and becomes a to the power 3. And then of course what I've done here is just apply the multiplication property. It gives me b to the power 9 and a to the power 10. Let us look at index law 6, which is the last one that we will consider. Let us compare the fraction 4 to the power 3 over 4 to the power 3. Now of course, according to the exponential notation, 4 to the power 3 is 4 multiplied by itself 3 times, and the same in the denominator. Now we could divide numerator and denominator by 4 3 times. So all these 4's in the numerator and denominator position actually becomes 1. So we get 1 over 1, which of course we know is 1. But if I apply the division rule, 4 to the power 3 over 4 to the power 3 is the same as 4 to the power 3 divided by 4 to the power 3, which is 4 to the power 3 minus 3, or 4 to the power 0. Now, in both these cases, we started with the same expression. So therefore, it simply means, or we can conclude, that 4 to the power 0 must be equal to 1. And this is an important principle. You could use your calculator and show that if you raise minus 3 to the power 0, it's 1. And even if we raise this complicated expression to the power 0, it's 1. But if we raise 0 to the power 0, it's undefined. So let's just test the correctness of that with the calculator. Let us look at the first one. We have minus 3, which we raise to the power 0. And that clearly is equal to 1. And then we have this quite complicated expression. We have a bracket, and within that we have a fraction. The numerator is the square root of 267, while the denominator is the cube root, so that's the second function of 197, and all of these we raise to the power 0. So what do we expect? We expect an answer of 1, which is what we get. And finally, what about 0 to the power 0? You do this with your calculator, and then your calculator will tell you this cannot be done. You get a mathematical error. Now, the reason behind this, to get 0 to the power 0, you need to start off, for instance, with 0 to the power 6 over 0 to the power 6. But then you divide by 0 to the power 6, which of course is 0. and you cannot divide by 0, so therefore it is undefined. We can now formulate this index law, namely that a to the power 0 is 1, provided that a is not 0. So now we know how to handle the case where the exponent is 0. So we've learned that if the exponent is a natural number, we can use the index notation. We also learned what to do in the case if it's negative. And we also know now what to do when it is 0. So therefore, if the exponent is an integer, we know how to treat it. Let us look at a few examples where we apply this index law number 6, namely that a to the power 0 is equal to 1 when a is not equal to 0. So in the first example, we have this quite complicated product to the power 0, and that of course is 1. You can test it with your calculator. Here again, in the square brackets, we have quite a complicated number raised to the power 0. It must be 1. Here we have some an algebraic expression, but because we raise it to the power 0, the answer will be 1. In tutorial 1, the focus is on the index laws. You are expected to use index laws to simplify the 8 expressions below here and leave answers with positive exponents. It is suggested that you pause the video, do tutorial 1, and after that view possible or suggested solutions. We first consider suggested solutions to problems 1 and 2. This was the problem given in 1. Now, firstly, I would change all negative exponents to positive exponents. So 3 to the power minus 2 must go underneath the line or move to the denominator position and becomes 3 to the power 2. In the same way, 4 to the power minus 2 becomes 4 to the power 2. You see, I treat the numerical exponential expressions first. Now, x to the power 5, there's nothing wrong with that, but y to the power minus 6, we will move down, and then it will become y to the power 6. Here you have a choice of two things. You could move this whole exponential base to the top and then simply change the sign of the exponent, or what I decided to do here is to use the law that allow us to get rid of this bracket. So the minus 2 as well as the 3 is multiplied by the minus 3. So you get x to the power minus 2 times minus 3, which is x to the power 6, and y to the power 3 times minus 3, which is y to the power minus 9. So now there is still the y to the power minus 9, which I will move to the top, where it will become y to the power 9. So now it is just a case of making use of the division exponential law. So we have 16 over 9. No further simplification is possible there. We have x to the power 5 above the line and x to the power 6 below the line. Now if you should use the division rule, then it's x to the power 5 divided by x to the power 6. So it's x to the power 5 minus 6, which is x to the power minus 1. So it becomes x to the power 1 below the line. Remember, if the exponent is 1, we never indicate it. Then, if we consider the base y, you have y to the power 9 divided by y to the power 6, which is y to the power 9 minus 6, or y to the power 3. From now on, I will not really use the division rule. I will simply observe that as far as the x's are concerned, for instance, there is more factors of x below the line, so we will end up with x to the power 6 minus 5 below the line. Furthermore, if you consider the base y, there is more factors of y above than below, so therefore we end up with y to the power 9 minus 6, or y to the power 3 above the line. In the second example, what I've done here, remember, there's more than one way to do this problem, or to solve this particular problem, as long as you stick to the particular rules. So what I've done is I've isolated the numerical coefficients. So it's 3 to the power 2, or 9, multiply by 2, and divide by 5. And then I grouped the exponential expressions with the base a together, and the exponential expressions with the base b together. So it's just a case of changing the order. Remember, the commutative law for multiplication will be valid. And then I grouped it because the associative property is also applicable to multiplication. So we have a to the power 4 multiplied by a to the power minus 2, and this a to the power minus 5 I bring to the top, and it becomes a to the power 5. So my strategy here is to bring everything to the numerator position. Then, as far as the base b is concerned, we already have b to the power minus 5 at the top, multiplied by b to the power 3 at the top, and this b to the power 6, which is part of the denominator, if it goes to the numerator position, it becomes b to the power minus 6. Now we can combine it. Of course, you should know that 9 times 2 is 18. I hope you don't grab a calculator for this. Divided by 5. The a's, now we use the property for multiplication. So all we do is simply add the indices. 4 plus 5 is 9, minus 2 gives me a to the power 7. The b's, so we get b to the power minus 11 plus 3, so it's b to the power minus 8. Remember, the instruction was that you must end up with an expression where all the exponents are positive. So what we still need to do here is to shift this b to the power minus 8 to the denominator position, where it will become b to the power 8. And this is then our final answer. Let us look at suggested solutions to problems 3 to 5. This was problem 3. So what I've done here is to use the commutative and associative properties for multiplication and get the numerical exponential expressions, the exponential expressions with base a and exponential expressions with base b together as groups. So we have minus 2 to the power 2. Be careful about this one. This one really means minus 1 multiplied by 2 to the power 2, and not minus 2 in brackets to the power 2, which will then be plus 4. So it's minus 1 times 2 to the power 2, or minus 4. 3 to the power 2 clearly is 9. Then we have a cube, or a to the power 3, multiplied by a to the power 5, and then b to the power 4 multiplied by b to the power minus 7. And then simply apply our law for multiplication. Of course, we should know that minus 4 multiplied by 9 is minus 36 without using the calculator. you combine the exponential expressions with the base a, so it's a to the power 8, and here b to the power minus 3. The only thing that's left is to make this negative exponent for the base b positive by moving it to the denominator position. One decision that you'll have to make is about the position of the minus. You could either leave it as part of the numerator or denominator, or in front of the fraction as a whole. This notation is what is normally suggested. In example number 4, we would just consider this particular one, which looks slightly different. The rest I've just left like that. Now this means 2 to the power 2 divided by 2 to the power minus 1. So use your division rule and it becomes 2 to the power 2 minus 1, so 2 to the power 3. And now I take everything to the top and combine the exponents where the bases are the same. So I'm leaving out a couple of steps here, so we get 2 to the power 3a plus 4 minus 3, because remember, if this goes to the top it becomes minus 3. Multiply by 3 to the power 6b plus 4, because again, if this one goes to the top, it becomes 3 to the power plus 4. And now you simply see if there is like terms that you can add. Of course, we can add the 4 and the minus 3 to get plus 1. And this is then the final answer. In example number 5, here we need to be very careful because you have some minus signs here. Now remember, there's two ways that you can treat this. You can either say that minus 2 is minus 1 times 2, so you have then minus 1 to the power 4 multiplied by 2 to the power 4, which of course is 16. Or you could put minus 2 in brackets to the power 4, which will also give you plus 16. In the same way, minus 3 can be treated as minus 1 times 3, which then, if you remove the bracket, becomes minus 1 to the power 3, which is minus 1, and 3 to the power 3 is 27. Or you can put minus 3 in brackets to the power 3. So then we multiply minus 3 by itself 3 times, and that's minus 27. And furthermore, you get x to the power 4 and x to the power 6. Now here I think I will allow you to use your calculator. I don't think many of us know immediately what is this answer. So firstly it's negative, and if you use your calculator, 16 times 27, you should get 432, and x to the power 4 multiplied by x to the power 6 is x to the power 10. Next we consider suggested solutions to problems 6 to 8. Now in problem 6, again I just want to repeat, there's more than one possible strategy. Here I've decided to remove this bracket here in the denominator position, so you get 3 to the power minus 2 and x to the power minus 2. And then I took all the focus on the numerical ones first, and this 3 to the power minus 2 I take to the top, so you get 3 to the power 3 in total, which of course is 27. What about the balance? There's various ways that's possible. So I've shifted this x to the power minus 3 to the bottom, and you get x to the power 3, and if I then use the multiplication law, I get x to the power 1. So this will be a possible way of tackling it. In the second example, here we see our friend to the power 0. So this particular exponential expression we immediately know is equal to 1. So we only need to focus on this expression to the power 5. Use our property, so you get 2 to the power 5, which is 32, x to the power 4 times 5, which is 20, y to the power 6 times 5 is 30, and z to the power 10 times 5 is 50. And the last one is the easiest of all these problems. The whole base here in the square bracket is raised to the power 0, and therefore the answer will be 1. In lesson 2 of this particular video, we will focus on exponential expressions and look at ways of simplifying it, and exponential equations, and consider ways to solve them. The outcomes for lesson 2. In this lesson we will, as mentioned before, simplify exponential expressions, and secondly, solve exponential equations. Firstly, we focus on simplification of single-term exponential expressions. We suggest the following procedure in this particular simplification process. Firstly, factorize all bases into prime bases, and your calculator can be useful in this regard. And then simply apply the exponential laws. Let us consider the first example. Note, in this example there is only numbers, so there's no variables. So we change 81 and write it in terms of its prime base 3, and it's 3 to the power 4. Like I said, if you have a problem, you can use your calculator. 27 as 3 to the power 3. Then apply the law which states that we can multiply these two exponents, so you get 3 to the power 4 times a quarter, which is 1, and 3 to the power 3 multiplied by minus 2/3, which is minus 2, and then use the multiplication law, which is 3 to the power minus 1, and then make it a positive exponent, which is then a third. In the second example, here we want to simplify the single term expression, but note that we have some variables here. The procedure is very much the same. 6 can be written as 2 times 3 in terms of its prime bases, 9 as 3 to the power 2, 18 as 2 multiplied by 3 to the power 2, and of course a quarter. You can write this as 1 over 2 to the power 2, which then becomes 2 to the power minus 2. Then remove the brackets simply by multiplying in the first bracket each of the exponents by 6. So you get 2 to the power 6x times 3 to the power 6x, 3 to the power 6x, here 2 to the power 4x, 3 to the power 8x, 2 to the power, and here need to be very careful. Both the 2 and the minus 2 must be multiplied by minus 2. So minus 2 times 2 is minus 4, and minus 2 times minus x is plus 2x. Then all I did is I put together the exponents for the same base. So we have at the top, and you can see I also got everything at the top, in other words in the numerator position. So you have 2 to the power 6x. This becomes 2 to the power minus 4x, and 2 to the power plus 4 minus 2x. And once they're all in the numerator, of course I use the multiplication property to get to this. Do the same for the base 3, so you get 3 to the power 6x times 3 to the power 6x, so it's 6x plus 6x, and this becomes 3 to the power minus 8x, so it's minus 8x. Then add the like terms. Now in this case you have minus 4x and minus 2x, it's minus 6x plus 6x, so the x's cancels out, so you only end up with 2 to the power 4, which of course we know is 16, and 3 to the power, that's 12x minus 8, so it's 4x, and therefore the final answer is 16 times 3 to the power 4x. Just to finish this off, let me use the calculator to show you how to get the prime factorization for a particular base, and I will only do 1 or 2 of them. Let's focus on 18. course, you should know that 18 is 2 times 9 and therefore 2 times 3 to the power 2. But if you don't know, you can always use your calculator. So simply enter the 18, enter it, and then use the prime factorization key, which is the second function key here, and it tells me that 18 is 2 times 3 to the power 2. I think that's enough of this. You should be able to handle this on your own. Secondly, we look at the simplification of polynomial expressions, exponential expressions. Now, the word poly means more than one. So what is the suggested procedure? If there's no variables, we use the previous strategy to simplify each term and then add. And if there's variables, you need to factorize. So in this first example, clearly there is no variables, it's all numerical numbers. So we apply the previous procedure to each of the three terms. So 125 in terms of its prime base. So base is 5 to the power 3. 16 is 2 to the power 4, and 8 is 2 to the power 3. And then we simply multiply the two exponents. 3 times 2/3 is 2. 4 multiplied by 3/4 is 3. And 3 multiplied by minus 2/3, right, is minus 2. Of course, 5 to the power 2. We simplify each term and then add, so that's 25. 2 to the power 3 is 8. Yeah, you must make this exponent positive, otherwise it's got no meaning. So this becomes then 1 over 2 to the power 2, which then means I multiply 2 by itself twice. And 2 times 2, of course, is 4. So you then get 33 minus 1/4, or 32 and 3/4. And if we have an example where you have variables, now you can see in the numerator position there is more than one term, so we need to factorize. Because remember, if you factorize, your number of terms become 1 and you end up with factors. So firstly, of course, I change the 9 and I write it in terms of its prime base, 3 to the power 2. Then you get 3 to the power 2 multiplied by x over 2, 3 to the power x. Okay, I've isolated that minus 1 there. You can write this as 3 to the power x times 3 to the power minus 1, and 3 to the power minus 1 is a third. Now, the type of factorization that I'm going to use here is to take out a common factor. So 3 to the power x is a common factor, and we end up with 1 minus a third, which you should know, right, is 2/3. Okay, and then of course this 3 to the power x and 3 to the power x can cancel out. So you get 1 minus a third, which is 2/3, divided by 9, which is 2/3 multiplied by 1 over 9. And that's 2 over 27. Just one thing. I could, in the case where there's no variables, use my calculator actually to check or predict the final answer. Let us just consider this once. Okay, let's use the calculator to check the correctness of this particular result. So I have 125 to the power, and the power is a fraction, in this case 2/3. Plus 16 to the power, and again the power is a fraction, in this case 3/4. And then subtract from that 8 to the power, and in this case the power is a negative fraction, so it's negative, and then a fraction, and the fraction in this case is 2/3. Right? Enter it, and you get 131 over 4, and I can convert this into a mixed numeral by using this second function here, and we get 32 and 3/4. So therefore, in the case of an example where there is no variables, you can use your calculator in two ways. You could upfront predict what the answer should be, or once you have done it, you can use your calculator to check the correctness of the result. You will get the opportunity to simplify exponential expressions. You are requested to simplify the exponential expressions in the 5 problems given here. I suggest that you pause the video, do tutorial 2, and then come back and view possible solutions. Let us look at a suggested solution to problem 1 of tutorial 2. You need to simplify this particular expression. The procedure, as mentioned before, is you need to factorize all bases into prime bases, namely the base 4, the base 16 and the base 32, and then simply apply the laws of exponents. So we write 4 as 2 to the power 2, 16 as 2 to the power 4, and 32 as 2 to the power 5. Then of course you use the law which allow you to simply determine the product of the two exponents here. So 2 multiplied by 3 over 2 is 3. 4 multiplied by 7 over 4 gives me 2 to the power 7, divided by, because 5 multiplied by minus 4 over 5 is minus 4, we get 2 to the power minus 4. So now we can change this division into multiplication by simply changing the sign of the exponent. Why can I do this? Because if you divide by 2 to the power minus 4, this 2 to the power minus 4 is really below the line. So it's part of the denominator. So if I multiply, I take it to the numerator position and thereby simply change the sign of the exponent. Now we have the product of 3 exponential expressions, or 3 numbers expressed in exponential notation. The bases are the same, so we can simply add the index numbers, and we get 2 to the power 14, or 16,384. Let us consider a possible solution to problem 2. You need to simplify this particular expression. The procedure again is to factorize all bases into prime bases. So you need to write 9 as 3 to the power 2, 27 as 3 to the power 3, and 81 as 3 to the power 4, and then after that apply the exponential laws. As suggested, I convert the bases 9, 27 and 81 to 3 to the power 2, 3 to the power 3 and 3 to the power 4 respectively, and then simply determine the product of the two exponential the two exponents here. So 2 multiplied by x minus 1. Remember, the x as well as the minus 1 needs to be multiplied by 2, so you get 2x minus 2. Here the 3 as well as the minus 2x needs to be multiplied by 3, so we get 9 minus 6x. And in the last case here, we multiply 4 as well as minus x by 4, so we get 8 minus 4x. Then what I've done in the next step, I took this exponential expression to the numerator position, and that can be done simply by changing the sign of the exponent. So if you take it to the top, it becomes 3 to the power minus 8 plus 4x. And then we multiply all 3. So in other words, we simply add the indices. So you get 3 to the power 2x minus 2 add to that 9, add to that minus 6, as well as minus 8 and plus 4x. Then all we do is add the like terms. Note we have 2x plus 4x, that's 6x, which will cancel out with a minus 6x. You got 9 minus 8, that's 1, and minus 2, so it's minus 1. Make the exponent positive, so it becomes 1 over 3 to the power 1, or a third. Let us look at a possible solution to problem 3 of tutorial 2. We need to simplify this particular expression. Remember, as suggested before, there is no variables here, so we simply simplify each term as suggested before and then add the corresponding answers. So as suggested before, the way to simplify it is to change to prime basis. So 4 gets written as 2 to the power 3, 9 as 3 to the power 2, after which we multiply both these exponents by 3 over 2, so you get 2 to the power 3 and 3 to the power 3. 125, you should know that this is the same as 1 over 8, which if I go to the prime basis, it's 1 over 2 to the power 3, or 2 to the power minus 3. Again, if we multiply these two exponents, you get 2 to the power 2. Now, of course, 2 to the power 3 is 8, 3 to the power 3 is 27, and 2 to the power 2 is 4. So the final answer is 4 and 8 over 27. A possible solution to problem 4 is discussed in this particular slide. Remember, here we have a polynomial and there's variables, so therefore the suggested procedure is that you need to factorize. So we write again in each exponential form in terms of its prime base. So 4 being 2 to the power 2, 4 to the power x then becomes 2 to the power 2x. So then it's pretty clear, because you can write 2 to the power 2x plus 1 as 2 to the power 2x multiplied by 2 to the power 1, or 2 times 2 to the power 2x. It is then clear, as I want to suggest, that you can take 2 to the power 2x out as a common factor in the numerator, and the remaining factor is 1 minus 2. And of course in the denominator, again, after you've added these two exponents, which results in 2 to the power 2x plus 3, or if you split it, 2 to the power 3 times 2 to the power 2x. Again, here you can take 2 to the power 2x out as a common factor, and we are left with 1 minus 8. So this then gives us minus 1 over minus 7, because you can see that 2 to the power 2x will cancel out, so the answer is then, because you have minus 1 over minus 7, the answer of 1/7. If we look at the last problem, problem 5 of tutorial 2, we can suggest the following solution. Again, remember, because you have variables and you don't have single terms, you need to factorize. By replacing 2 to the power x with a, the numerator expression becomes then a squared minus a minus 6. I hope you can see that. And therefore the numerator is really a trinomial. It's a trinomial in 2 to the power x. So if I factorize this, I get a plus 2 multiplied by a minus 3, and then back substitute, in other words replace a by 2 to the power x. We can then see that this is the way we can factorize the numerator. Of course, then there's a common factor of 2 to the power x plus 2, which can cancel out, leaving us with 2 to the power x minus 3. In this slide, we start our discussions on how to solve exponential equations. You could use your calculator to complete the following table, or you can do it without the calculator, and then express the powers with negative exponents as fractions. Let me take a few examples. For instance, if you have y equals 2 to the power x and x is minus 3, then we get 2 to the power minus 3, which of course is a negative exponent, and that you can write as 1 over 2 to the power 3, or 1/8. Right, so that's exactly what is requested here. Just to show you how you could use your calculator, if for instance x is minus 3, then 5 to the power minus 3, you can calculate that with your calculator. Remember, we know that this is 1 over 5 to the power 3, and you should know that 5 to the power 3 is 125. But the calculator will help you straight away with this, showing that 5 to the power minus 3 is 1 over 125. So whatever way you choose to complete this table, the first assignment is to complete the table. Now we can use this table to determine solutions for the 6 questions that I've listed here below. Now from the table it's pretty clear that we can consider 2 to the power x, or 4 to the power x, or 5 to the power x. So the question is, what is the solution of 2 to the power x equals to 16? Now 2 to the power x equals to 16, you will get 16 when x is equal to 4. Right, can you see we haven't got the 4 here, but the next one in this particular table, if the exponent is 4, will be 16. So 2 to the power 4 is 16. Now what do we notice now? We have 2 to the power x equals to 2 to the power 4. Now the bases are the same, so clearly the exponents must be the same. So x is equal to 4. So this one specifically is really not in the table. The next one you will find in the table. You need to solve 2 to the power x equals to 1 over 8. And there it is. We see this is the case when the exponent is minus 3. So 1 over 8 is 2 to the power minus 3. Please, you don't really need the table. You could say that 1 over 8 is 1 over 2 to the power 3 going to prime basis, which is then 2 to the power minus 3. Bases, again, are the same because they both equal to 2. Therefore, exponents must be the same. In other words, x must be minus 3. Just a bit of advice. Once you get this solution, you can back substitute to check the correctness of that. If you get here in the first case that x is 4 is a solution, if you replace x by 4, you get 2 to the power 4, and 2 to the power 4 is equal to 16. In the case of 4 to the power x equals 1, this is where the exponent is 0, so you replace 1 by 4 to the power 0, so therefore bases are both equal to 4, therefore exponents must be the same, x equals to 0. In example 4, we have 4 to the power x equals to 1 over 64, which is this case where the exponent is minus 3. So 1 over 64 is 4 to the power minus 3. Again, I would like to stress that it's important to note that you don't really need the table, because 64 is 4 to the power 3, and therefore we get 4 to the power minus 3. So therefore, because the bases are the same, the exponents must be the same. X is therefore minus 3, and remember you can test the correctness of that. 125 in the case of base 5 is 5 to the power 3. So clearly, therefore, x must be equal to 3. And in the last example, 1 over 25, we get that when the exponent is minus 2. So we have 5 to the power minus 2, therefore x must be equal to minus 2. We now look at a general discussion on the solution to exponential equations. Now, equations like y equals 2 to the power x, y equals 4 to the power x, and y equals 5 to the power x are exponential equations. And this is the type of equations that we would like to solve, where we will pick specific values for y. So in other words, we will solve exponential equations of the form a, where a in this particular case was 2, 4, or 5 to the power x, equals to b, where b is a specific value for y. We will not consider the case where a is equal to 1, because 1 to any power is always equal to 1, so it's trivial. Nor will we consider cases where the base is 0, that will be undefined, and not cases where the base is negative, because if the base is negative, then in some cases when the index is even, it will be positive, but if it's odd, it's negative. So we will strictly look at a positive basis. So what is the solution strategy? Now, if we have a to the power x equals to b, our objective is to write b in the form a to the power n. In other words, in terms of the same base. And then, if the bases are the same, then the exponents must be the same. So x must be equal to n. So we will always try and change the bases to such an extent that they are actually the same. So identical bases implies that the exponents must be the same. Now here is a sketch of the exponential equation y equals 2 to the power x, and I've just indicated a few of the important points on this exponential growth function. For instance, if we say y equals 2 to the power x, what will happen if y is equal to 8? So when y is equal to 8, it is clear that x will be equal to 3. Because all we do is we write 8 as 2 to the power 3, and therefore the bases are the same, and the exponents must then be the same. So therefore x will be equal to 3. Let us look at a few examples on solving simple exponential equations. So in this next two equations, the equations will be in the form a to the power x equals b. Our solution strategy will be to convert b in the form, or to the form a to the power y. Because if the bases are the same, the exponents must be the same, and therefore x will be equal to y. And once you've finished, it is suggested that you test the correctness of your answer. So let's apply it to this particular case. So my b in this case is 1 over 32. So I need to write this in the form 2 to a certain power. Now, of course, 32, you can use your calculator and you'll see that it's 2 to the power 5. So we get it is 2 to the power minus 5. So therefore bases are the same. So according to this strategy, x must be minus 5. Then I can test the correctness. I'll start off with the left-hand side, which is 2 to the power x, and replace the x by the suggested solution of minus 5. So we get 1 over 2 to the power 5, which is 1 over 32, and that is equal to the right-hand side. So we know that the solution will be correct. In the second one, here we have the product of two different bases. So we need to go to prime bases throughout. And of course, throughout the prime base will be 3. So we write 9 as 3 to the power 2. So you get 3 to the power 4x. 27 as 3 to the power 3. So you get 3 to the power 3x minus 3. Remember to multiply the x as well as the minus 1 by 3. And 81 as 3 to the power 4. Putting this two together, you get 3 to the power 7x minus 3, because if you multiply, you add the index numbers. Now the bases are the same, therefore the exponents must be the same. So in other words, 7x minus 3 must be 4. 7x is therefore equal to 7. X is therefore equal to 1. You should know how to solve a simple linear equation in one unknown. How do we test it? Well, the left-hand side, if we replace the x by the suggested solution, you get 9 to the power 2 and 27 to the power 0. And 9 to the power 2 is 81 and 27 to the power 0 is 1, and that is 81, and that's equal to the right hand side. So we know that x equals to 1 is the correct solution. Next we look at an exponential equation where preliminary factorization is needed. So if, like in this case, it's necessary, you first need to factorize certain algebraic expressions. Then you may end up, or hopefully end up, with an equation of the form a to the power x equals b, and then we use our well-known strategy by now by changing b to a to the power y, and then of course x must be equal to y, and then test the correctness of your answer. Let's look at this particular example. Now 25 to the power x of course is 5 to the power 2x. Now that you can write as 5x all squared minus 1, which then makes this a difference between two squares, and you should know how to factorize that. So as I mentioned, that 25 to the power x is 5 to the power 2x, or more specifically 5 to the power x all squared. So therefore we factorize the numerator as the difference between two squares, and then the 5 to the power x minus 1 can cancel out, and we end up with 5 to the power x plus 1 is 3126. So we need to take this 1 to the right hand side, and then it's in the form a to the power x equals b, while this b we change to 5 to the power 5. Now the bases are the same, therefore the exponents must be the same. So it seems that x equals to 5 is a possible solution. We just need to test the correctness, and here you can use your calculator to test it. If x is 5, so 25 to the power 5 minus 1 over 5 to the power 5 minus 1 turns out to be 3126, which is equal to the right hand side. In the second example, where preliminary factorization is required, we will follow exactly the same 4 steps as before. In this case, we find that the numerator is a trinomial, because remember, 2 to the power 2x is 2 to the power x all squared. So this is a trinomial in 2 to the power x. We had an example like this before. So therefore you factorize the numerator as a trinomial in this way, and then 2 to the power x minus 3 can cancel out, and we get 2 to the power x plus 5 is 37. We need to get it in the form a to the power x equals b, so we subtract 5 from both sides. Therefore 2 to the power x is 32. Now it's in the form a to the power x is b, and b, the 32 we can rewrite as 2 to the power 5. Again, you could use your calculators, and then clearly from our solution strategy x must be equal to 5. And then all that is left is test the correctness. Here you can use your calculator. So if x is 5, we get 2 to the power 10 plus 2 times 2 to the power 5 minus 15 over 2 to the power 5 minus 3. If you input this in your calculator, you find you get an answer of 37, which is the right hand side. So therefore this must be the correct solution. In this exponential equation, we want to find an approximate solution. In other words, we cannot get an accurate solution. If you look at the example where you have 3 to the power x is 66, now 66 cannot be written exactly as in terms of the base 3. And you are requested therefore to determine the solution correctly to 2 decimals by means of the trial and improved problem solving strategy. It should be clear that 3 to the power 3, because it's 27, and 3 to the power 4 is 81, is such that 66 lies between these two. So 66 is therefore 3 to a power slightly greater than 3 but smaller than 4. So at least we know the solution must lie in the open interval from 3 to 4. So we need to try and find solution. So I select x values from 3.1 up to 3.9, and you can see I go up with intervals of 0.1 and then use the calculator to calculate the output values. Let me show you how to obtain this particular table by means of your calculator. Okay, so once you've got the calculator here, we switch to the table mode, and you are requested to enter the defining equation, and that's of course 3 to the power x. Now remember, it's not the multiplication but the little x there, which is part of the alpha key. Okay, once you enter this, it will ask you where to start. Now obviously we want to start at 3.1. Where do you want to end? We want to end at 3.9. And the third question is, what is the steps? Now we go in steps of 0.1 or just 0.1. Once you enter this, you will immediately get the table. So 3.1 gives an answer of 30.135. 3.2 as 33.634. So now we can record these results, and then observing these particular results, we see that if we get to 3.8, it is still less than 66, but when we get to 3.9, it's greater than 66. So therefore, the solution must lie between 3 to the power 3.8 and 3 to the power 3.9. So, or it must lie in the open interval from 3.8 to 3.9. So now you use your calculator and you refine this. So again, I will use my table mode. If you go back there, all you really need to do is to say where do you want to start. You want to start at 3.81, and where do you want to end? You want to end at 3.89. Alright, and which steps do we want to take? That's of course 0.01. Now I've just put a portion of that particular table here, and from these values here, it is pretty clear that 3 to the power 3.81 is still less than 66, but 3.82 is greater. So I can refine it a little bit more. I can therefore say that the solution must lie in the open interval stretching from 3.81 to 3.82. So further refinement is therefore required. So again, I use that same table, and I start off, you don't need to change the equation, it's still the same. Calculator will ask you where must you start, and you will say I'll start at 3.811. And where do you want to end? It's 3.819. And then I've just selected a portion out of that, which indicates to me that 3 to the power 3.813 is still less than 66, but the next one is greater than 66. Now remember, we were requested to find it accurately to 2 decimal places. That doesn't matter which of these two you consider. We can see that x must be 3.81. That's therefore the solution correct to 2 decimal places. You are now ready to tackle our last tutorial, tutorial 3, in which you need to solve exponential equations. So you are given the 4 exponential equations here, and you need to solve them. Note, you will still use your strategy as suggested before. in examples 2 and 3, you will have to do preliminary factorization, and in the last one, it is an estimated solution. So I suggest that you pause the video, do tutorial 3, and then come back and view possible solutions. Let us look at a possible solution to problem 1 from tutorial 3. We need to solve this exponential equation. So the first step will be to write all the bases in terms of their prime factorization. So 27 is 3 to the power 3, so you get 3 to the power 3x plus 6. 81 being 3 to the power 4, we end up with 3 to the power 8x minus 4. Now the bases are the same, so according to our strategy, the exponents must be the same. So we therefore end up with a linear equation in one unknown, and you should know how to solve it. I can take the x's to one side. If I take the 3x to the right hand side, I get 5x, and if I take the minus 4 to the left hand side, I get 10, and then swap the two sides. So 5x is then 10, or x is equal to 2. All that is left now for us is to test the correctness of the solution. So if you take the left hand side, 27 to the power 2 plus 2, or 4, your calculator will tell you that's 531,411, and then you do the same with the right hand side. 81, if x is 2, we get 81 to the power 3, and using your calculator you get exactly the same result. Therefore the left hand side is equal to the right hand side, so therefore x equals to 2 will be a solution to the given exponential equation. Let us look at a possible solution to problem 2 of tutorial 3. If we look at this, then 16 to the power x minus 1, because 16 can be written as 4 to the power 2 to the power x, or 4 to the power 2x, or 4 to the power x all squared, then this is the difference between two squares. So we can factorize this as 4 to the power x plus 1 and 4 to the power x minus 1. 4 to the power x plus 1 can cancel out, so you get 4 to the power x minus 1 is 4095. Add 1 to both sides, then we have it in the form a to the power x is equal to b, and this 4096 can be written as 4 to the power 6, so therefore clearly x must be equal to 6. You could, of course, instead of working with the base 4, you could have worked with the base 2, and you'll end up with exactly the same answer. Testing it, if we replace x by 6 in the left hand side here, you get 16 to the power 6 minus 1 over 4 to the power 6 plus 1. Use your calculator, you will then get an answer of 4095, which is equal to the right hand side. So therefore x equal to 6 is a correct solution to this exponential equation. If we look at problem 3 from tutorial 3, we note that the numerator is a trinomial which can be factorized in this particular way. And then clearly 3 to the power x plus 2 can cancel out, and then adding 5 to both sides, we get it in the form 3 to the power x equals to b, or a to the power x equals b, but this b, or 81, can be written as 3 to the power 4, so according to our strategy x must be 4. Testing it, in other words, replace x by 4 in the left hand side of the given equation, and you get 3 to the power 8 minus 3 times 3 to the power 4 minus 10 over 3 to the power 4 plus 2. Input this in your calculator, it will give you an answer of 76, which is equal to the right hand side, so therefore this will be the correct solution. If we look at the last problem of tutorial 3, we need to determine the solution to this exponential equation correct to 1 decimal. And now, because 2 to the power 4 is 16, while 2 to the power 5 is 32, it is clear that 27 must lie between 2 to the power 4 and 2 to the power 5. So therefore the solution to this equation must be in the interval, open interval from 4 to 5. So as before, I can use my calculator in table mode, inputting the equation y equals 2 to the power x, starting at 4.1, ending at 4.9, and taking steps of 0.1 will then give us this particular table. Now if we study this very carefully, we find that if we have 2 to the power 4.7, it is still less than 27, but the minute we pick 2 to the power 4.8, it's greater than 27. So therefore clearly the solution must lie in the open interval from 4.7 to 4.8. So we need to refine it a little bit more. So because we want it accurately to 1 decimal, we must be sure of the second decimal. So further refinement, I go to my table mode. Remember, I don't have to change the equation, but my starting point will now be at 4.71 and my end point will be at 4.79. And I will take steps of 0.01. If we do that, we find that if we have 2 to the power 4.75, it's slightly less than 27, while if we have 4.76, it's just greater than 27. And this is as far as you need to go with this particular table. Because if we want to get the answer correct to 1 decimal, we must be certain about the second decimal, and it doesn't matter if it's 5 or 6. It will both mean that you will up or round it up to 4.8. So therefore that solution lies in that interval, and therefore x equals to 4.8 is a solution correct to 1 decimal. We have come to the end of the video on exponents. Please remember to consult textbooks for additional examples. Attempt as many possible other similar examples on your own. Compare your methods with those that were discussed in the video. Repeat this procedure until you are confident. Please do not forget, practice makes perfect, and that is the only way that you can learn mathematics, but please only practice once you understand the basics. Goodbye.